Imagine what happened when the very first strangers met, back before smartphones, before cities, before the wheel. What could these two people, tribal nomads with nothing in common, ever hope to talk about? I imagine that it's the same conversation that happens between strangers in our modern world. In fact, it's our favorite conversation starter to this very day. It's the weather. I'm Blakely Thomas Aguilar, and this is Pop Culture Tech, an original podcast brought to you by VMware. The saying goes that the only certainties in life are death and taxes, but you could argue that it's actually death, taxes, and weather. The weather is perhaps one of the only universal things we all have in common. It affects us, sure, in different ways depending on where we live or travel, but from the beginning of time, humanity has been obsessed with the weather. Native peoples had shamans to call rain that nourished crops. Local weather experts are celebrities with features on billboards. A weather app is one of the few standard features on all new smartphones, regardless of manufacturer. I'll be honest with you, I've never been that interested in the weather, personally. I downloaded an app because it allegedly accurately predicted within minutes whether it was going to rain out a baseball game. I occasionally watched the Weather Channel when a particularly violent system was rolling into town. That was until I saw something truly amazing. Hurricane Florence in 2018 caused over 1 million people to evacuate the east coast of the United States. Like so many of you, I tuned in to watch the drama unfold. I saw a woman standing in front of a green screen, but instead of the standard splotches of varying colors on a flat map, I saw the water beginning to rise around her. It started at her ankles and gradually, slowly rose to her hips and then her chest. The water around her filling with swirling debris, cars, telephone poles, rooftops, entire houses became submerged. And as the wall of water rose yards above her head, positively towering over her, I was filled with terror. From my couch, hundreds of miles away, technology made this emotion possible. The jaw-dropping innovation that was green screen a few decades ago has blossomed into an immersive experience that enables us all, even those not in the eye of the storm, to experience what people halfway across the world are living through and struggling to survive. Yet what you see on the screen isn't even a portion of the innovation that's required to bring those predictions into our homes and onto our smartphones. That's the magic, the pop culture tech behind the weather. Stephen Hawking said, "There is no way that we can predict the weather 6 months ahead beyond the seasonal average." But that hasn't stopped some of the brightest minds from trying to prove Hawking's prediction wrong. Two of those people are Dr. Amy McGovern and her team at the University of Oklahoma, and Yuval Gonkarowski, Chief Technology Officer at Climacell.
When I got up in the morning today, and I live in Cambridge, I work in Boston. I was almost tempted, and I as I've done my entire life, to ask my favorite weather companion, what's the weather going to be like in Boston today? But that's not really what I wanted to ask, right? What I wanted to ask is, what is the weather going to be like between the street that I live in, Cambridge, in the route that I take to commute to work in Boston between 7:30 and 7:55, which is exactly when I'm in the car driving or when I'm outside walking my dog before I go to work or whatever. So I think that inherently as people, we're already giving our weather providers a discount just by the way we engage with them. Because the reality is that today technology has advanced enough, and Climacell is leading those efforts to really be able to tell us what is happening on a street level on a minute by minute basis. And when we talk on a city level, when I ask Siri, what's the weather going to be like in Boston? And then I ask Siri, what's the weather going to be like in New York? Those are kind of arbitrary measurements, right? How bigger is New York than Boston? We're used to thinking on a city level, but that's not really what we want. What we want is our city, our street, in that specific point in time. I'm going to go to lunch in an hour and a half. I want to know exactly what the weather is going to be like outside the Climacell office at noon when I go grab my sandwich. So I know if I should take my jacket or my umbrella. And then beyond that, we can think about seasonal or subseasonal. So is this winter going to be colder or warmer than past winters? And that, of course, has implications on anything from, ski resorts all the way to commodity trading.
I grew up in Ohio, or at least for part of the time. I didn't, my dad's is military, so we moved a lot. But there was a microburst that hit our house, and there was no forecast. There was nothing. We literally were out and we came home, and there were a whole pile of trees down on our house. And it really is a tremendous difference in our capability to forecast these days. I'm not actually a meteorologist. My background is actually in computer science. That's what all my degrees are in. But I find the meteorology particularly fascinating because it's a way that we can use our computer science and our machine learning to actually make a difference to the real world. And weather is really important across the entire United States. Everybody experiences weather, so we can use our knowledge to improve prediction and actually save lives.
Unlike the shamans from hundreds of years ago, weather prediction isn't magic, it's science, but it's also a business. The global weather forecasting systems and solutions market size is expected to reach $4.63 billion by 2025, according to a study conducted by Grandview Research. This market is fueled by technology, from the sensors on cell phone towers and at airports, on ocean banks and satellites orbiting our world. Yet, like so many industries today, the real foundation behind weather forecasting and predictions is less about the hardware, the sensors, the satellites, the computers, and it's about software and code. And just as future technologies impact so many other industries, recent advancements and, basically, the coolest things happening today are fueled by artificial intelligence.
So I use artificial intelligence and machine learning techniques to improve the prediction of the severe weather. So we primarily over the last few years been focusing on tornadoes and wind and hail. Artificial intelligence and machine learning, they're related to each other. If you drew a Venn diagram, which is really just a circle showing what's inside different things, AI would be a larger circle than machine learning. So machine learning is about algorithms that learn to adapt to the data over time. Artificial intelligence can include non-adaptive algorithms. So search techniques, for example, such as Google Maps. I don't actually know exactly what Google Maps is doing behind the scenes because that's not uh, published. But I yeah, I teach the algorithms that I assume that they are using, and those are search algorithms. And then machine learning is taking data in, and then it's learning to adapt what it's doing over time. So, for example, the smart cars that are driving around, they're learning what it means to see this particular set of sensor readings, and it means that there's a ball crossing their path, that there's a pedestrian crossing their path.
But there are techniques that we can use to really get amazing observations from really anything. So take our microwave signal technology, for example. We're talking about fixed towers, so cellular towers that talk from tower to tower. We talk with our partners that give us really this diagnostics data that is just really the signal strength. There's no privacy element attached to it at all. And by looking at how the signal strength changes based on the medium that the signal travels in, right? So water will absorb or scatter the energy in predictable ways. We can reverse engineer that to tell us the weather.
So in our case, we're taking in all of the weather models and we're learning how we need to adjust the output of the weather models. Basically, the hail forecasting example, we are not rerunning the models. We're taking the output of the models, which are already based on physics, and we're post-processing them to improve the spatial and temporal biases that might come out. So for example, perhaps the model put the hail all too far west, and we're trying to improve the post-processing to move the hail where we believe it really should be. And the way that involves machine learning is that you take hundreds and hundreds of examples of what the model said would happen and what really happened, and you learn to adapt what really should have happened based on what actually did happen.
Machine learning is a hungry technological beast. ML needs data, information, to work, to help scientists and technologists find the answers they're looking for. With weather predictions, I was incredibly surprised to learn that those data sets, all that information, comes primarily from one source.
I guess the weather world is maintained, or mostly, the bigger players there are either governmental institutions or other non-for-profit or academic institutions. For example, take the United States. You have NOAA. You have the National Center for Atmospheric Research, which is a semi-academic body. And other countries that they own the radars are government owned, or part of the defense industry or other stuff. So a lot of these things are really publicly owned or publicly driven. And sometimes it may not make sense for that to be economically feasible for a private company if you were to go and deploy hundreds of thousands or millions of weather stations.
The data primarily is coming from the government. So, it's particularly the hail one that I was talking about, we have access to the operational feed that they're testing, two different models that will become live quickly. One of them is live now, one of them is planned to be live over the next few years. So, we're getting that data entirely from NOAA. The storm reports that are coming in are also coming in from NOAA. We have other work that doesn't involve just the hail work. So, for example, our tornado work is using stored historical archives of radar data across the entire United States. You're asking for technical details. This is terabytes and terabytes of data, because you basically are looking at 3D volumes of data across the entire United States. So it's a tremendous amount of data. There's still the people aspect involved, because the people are the ones who create the tornado reports or the hail reports or the wind reports. And they're the ones who have to also make sure that they are quality controlled. And sometimes things get missed. Sometimes the report is off by a little bit in space or in time.
Basically, the challenge here is to take in these millions and millions of observation points on a minute by minute level basis without, one, emptying the wallet very quickly, and two, looking at every observation in the way that it should be looked at. So it's not an all animals are equal case. It's a case of some animals are more equal than others. And some observation points in certain aspects of time and certain aspects of weather and certain aspects of geography give us more data or give us insights into the things that we want to look at that specific point in time. It really is a data game. And in 2019, if you own the data, you can do amazing things with it.
But we only started collecting data in digital form a few decades ago. Weather has been around since our world was formed. And if we only have a few decades of digital data stored for use, how can we truly, really predict the way our world and our weather works? Will there be another ice age? Have sea levels risen like this before? And what happens after? And if global warming occurred in our world's past, what can we learn from that historical data to help us prepare for our future? To help us answer these big and incredibly important questions, I reached out to Dr. Kim Cobb, professor of Earth and Atmospheric Sciences at the Georgia Institute of Technology.
I spend my time looking into the past, especially with regard to extremes of ocean temperatures related to El Nino events, and how those have varied over the last centuries and how they're changing today and what that means for our future. And so I spend a lot of time in coral reefs in the deep tropical Pacific, recovering those samples and trying to understand the impacts of climate change at those sites. And have a lab here that we use to analyze those samples and extract those records. We have spent 20 years over many, many expeditions and tons of samples and tens of thousands of data points to try to constrain what is a very high background of variability for the natural climate system, which is involved with El Nino. And so it has periods of being very active and being very quiet. And so it's taken us all of 20 years to amass enough data to not fully characterize, but better characterize the natural background of this climate cycle in order to identify that something different is going on today. The last several decades of data do stand out as significantly stronger variability than the pre-industrial era. This is a very important line of investigation, which is maturing very, very quickly. That's basically trying to integrate all of the amazing information we have about past climate and use it in concert with climate models to understand where we're going over the next decades. So, what do models say about past climate variability in our region and its drivers? And what does it say about future climate change and the nature of variability we might expect? And how can we make quantitative comparisons between our small data and those very big data sets, so that we can take our data and understand the full dynamical context of what they're trying to tell us. And so that's where we get into kind of advanced statistical analyses of these kinds of data sets. We use spectral analysis to extract oscillatory signals and define how much decadal versus another kind of variability is driving our record. Obviously looking to see how our record relates to rainfall and temperature and currents and atmospheric circulation, so that we can understand kind of how to read this rock record in a model framework that is physically grounded. So there's some big data aspects to our work, and there's some kind of very small data aspects to our work. And part of the challenge and the fun is working between those scales and doing it hopefully in robust and novel ways to advance the field. What the state of the art really is right now is more akin to what's going on with weather forecasting, where we are actually trying to assimilate time step by time step the network of available paleoclimate records through time and train a model to move through that network in a dynamically consistent fashion, right? Informed and anchored to that network signals, but have it evolve time step to time step on its own 2 feet and its own dynamics to give us the best representation of what the global climate system may have done in obviously before we had satellites spinning around the Earth. And so that framework of kind of climate data assimilation is something that has already been applied to generate gridded climate fields back to 1948, where we can have, any field you want, anywhere you want, it's going to be available from this assimilated products, in that case of instrumental data. If we want to go back 1,000 years, though, we're going to have to use paleoclimate data. And so that's where the field is going right now. How can we capture the richness of all of these different kinds of archives and inform a global climate simulation to represent what might have been global climate at every grid box with every variable over 1,000 years.
The big question now is, with all this data, all this information, whether it's manually entered into the digital data stream like Dr. Cobb's or automatically collected via satellite and weather sensor, how do weather technologists transform all that noise into real, accurate predictions? The answer? Math, physics, and really, really fast computers. Something that Dr. McGovern knows a lot about.
So we generally are using supercomputers to do all of this work. There are different supercomputers available at the University of Oklahoma, so different work is being done on different supercomputers. But in all cases, because we have so much data that we're storing, and then a fair amount of processing that you need to do to actually train the model, we're using supercomputers. One of the cool, innovative things that I think is going to make a real difference over the next 5 to 10 years, and they're not quite ready for it, so this is research now, but 5 to 10 years, is that they are working on using machine learning to improve the models itself. So I mentioned earlier that the models for the numerical weather models are based on physics, but then once you actually go to run the simulation, it's really computationally expensive. For example, if you're trying to simulate 30 seconds of storm time, it might take you 4 minutes to simulate that. That's computationally expensive. If you want to simulate something in real time and it's taking 4 times, 10 times as long, you're computationally expensive. If you want to simulate 30 seconds of storm time so you could do a prediction, you need to be less than 30 seconds in computational time. So we have to do all this processing of the data because it's raw. And the other is that the data is located all across the US, and just ingesting the data takes time, right? You would like your supercomputer to be next to the data input so that you literally can just get it quickly. And right now, if you have to move it across the United States, yes, it looks really fast to the consumer, but it's not really fast when you're moving terabytes of data. Supercomputers are expensive, right? And we're working on the other innovation that's going to come about is that a lot of people are starting to work on using the GPUs. And the GPUs have done a tremendous amount for vision, for computer vision. And people are working on getting the GPU usage in the numerical modeling world. And I think that's also going to bring about an innovation, and it will make the models cheaper and faster. And almost everything has math underlying it, and that's what the GPUs are really good at. They're really good at doing math quickly. And even if people don't realize that their computer is doing math in the background to do something, it is.
So far, Hawking is right, but no real surprise there. Dr. McGovern and her team are striving now to make it possible to accurately predict whether a tornado is possible 12 to 24 hours in advance, a far cry from 6 months. But with technological leaps happening far faster than ever before, we are closer to significantly advanced outlooks than ever believed. But that gets to the core of humanity's obsession with weather. It's absolutely about whether we're going to need an umbrella or if we need to pack sunscreen. But it's also about human life and experience. It's about saving friends, neighbors, and even that perfect stranger halfway across the world.
Sure. And so this is a very important line of investigation, which is maturing very, very quickly. That's basically trying to integrate all of the amazing information we have about past climate and use it in concert with climate models to understand where we're going over the next decades. And so how does that work? Basically, what we're trying to do, I sit on the lead author team for the Intergovernmental Panel on Climate Change, and they consolidate the body of scientific evidence to inform policymakers and stakeholders around the world about what to expect with climate change. And when they say that you should prepare for a given impact, if you don't, you are putting your economy and your citizens at risk. And so this is the body that the global community turns to. And so what they're in the business of doing is try to figure out what signals are emerging from the background of natural climate variability, and can we link those to greenhouse gases? And when those two pieces come together, with enough studies supporting those lines of results, then the IPCC will make a fairly definitive statement, moving a set of impacts into a column of likely impacts or very likely impacts or virtually certain impacts. And communities around the world can use those to design projects around adaptation to coming threats, or of course, invest in reducing emissions to decrease the likelihood of those things getting worse in the future.
When we think about places like emerging countries or folks that have been less fortunate at getting weather at their fingertips, I don't think that anywhere in the future a company is going to come and say, okay, I'm going to deploy a full network of sensors to give the citizens of those areas what they need and should get. And our approach is, because the signals are already there, we're happy to provide those people with that opportunity, so that anyone anywhere in the world will be able to get up in the morning, know what the weather is going to be like in their street, in their city, in their neighborhood during the day, and plan their day accordingly. And I think that's, we can't forget the social impact that that's going to have.
Oscar Wilde famously said, "Conversation about the weather is the last refuge of the unimaginative." If he could have journeyed 150 years into the future, he might not be thinking the same thing. I'm Blakely Thomas Aguilar, and this is Pop Culture Tech. A special thanks to our guests, Dr. Kim Cobb, Dr. Amy McGovern, and Yuval Gonkarowski. This podcast is brought to you by VMware, the software that connects, automates, and secures the world's digital infrastructure. Learn more about our podcast at vmware.com/radius. And you can follow me and ask questions about this episode and more at Blakely Ags on Twitter. Until next time.